Okay, so okay, so let us start the last lecture for today. Tameness beyond o-minimality. Philipp, go ahead.
Thank you very much. Good. Okay. So first of all, thank you for having me, and thank you for giving me this opportunity to advertise now the third module of the Tameness beyond o-minimality of the graduate course Tame Phenomena of the Real Field. So I think Chris gave a few hours ago when I was teaching still in advertisement for his module of this graduate course, and so I will follow up on his. Just a warning, I'm not sure whether this is something good or bad, but this is because this advertisement for a graduate talk or for a graduate course, this talk is focused for an audience of graduate students, whether they are now here or maybe someone is watching it on YouTube, but maybe we all consider ourselves as graduate students for now. The module itself will be the last one, so this will be starting on March 14th and go to April 8th. And I really, really hope that I can be in Toronto to give it there, and hopefully we'll be through many of this until then. I will in this talk say a little bit about Tameness phenomena of the real additive group. So you can see that the graduate course is entitled Tame Phenomena over the Real Field, and therefore the graduate course I will really stay over the field. But I will also say a little bit about Tameness phenomena over the real field, because first of all, I think it connects very nicely a little bit to what Ian said in the last hour, and also what Alexei will say, I think, on Wednesday. This talk, and this is really important to me, also serves as an invitation to the Tameness research program, or the Tameness program as Chris usually calls it in general. So in particular, if I think back on the time when I was Fields 10 years ago, I think one of the great things about the Fields Institute and as such a program is that you can talk to researchers in various different areas, and maybe something that might interest you in some other areas that you haven't worked or haven't thought about yet. And so consider this talk also an invitation to talk to me if you're in Toronto, or talk to, if I'm in Toronto and you're in Toronto, or shoot me an email, or talk to Chris, who is already there now, and maybe you come to him. So this should be not only be something for the graduate course, but also for the kind of an invitation to this research program as I see it. As you might know, Fields for these thematic programs, you can have these kind of ad hoc organized mini workshops. These are not supposed to be like this workshop where we invite people and everyone comes. It's more so that when people are around, we organize this mini workshop and talk about things. I've spoken with Pantles, and he's also planning to be there if this is possible during the end of March. And so we would like to organize then kind of one of these ad hoc mini workshops around this topic. The dates are still flexible, but I think that's the idea behind all of this. I also want to take the opportunity to say thank you to many people. I mean, first of all, I think to the Fields Institute, because I think this is really an outstanding institution, which I have benefited so much. So when was it now? 12, 13 years ago, when we had the thematic program on nominal structures and real analytic geometry. I've benefited immensely from being there as I think I just finished my PhD, and I know many others too. I've benefited, of course, not just from the Fields Institute, also from all the senior people who were there. And although I somewhat consider myself in my mind as a slightly advanced graduate student, I now have to consider myself also somewhat senior. So if I'm very happy to pay this, what I received then forward. So if the younger people want to talk about stuff, then I'm more than happy to do so when I'm in Toronto, but also before. It's a little bit harder, of course, and it's very unfortunate that we're in this pandemic have to be online. But still, if there is something, if you like what I'm talking about, or maybe if you don't like, shoot me an email, we can talk about this. Okay, so this is all the kind of announcements, and so now I really start. Okay, so here's two of my favorite quotations from two of my favorite mathematicians. So the first one is from Lau. I think he wrote this in one of his surveys about o-minimality, actually. So what he wrote, and this is kind of sets a tone also for this kind of more general tameness program that I want to introduce here, is the following. So a lot of model theory is concerned with discovering and charting the tame regions of mathematics, where wild phenomena like space-filling curves and Gödel's incompleteness are absent, or at least under control. As Khrushchevsky put it recently, it's a little bit too long ago, but model theory is equal to the geography of tame mathematics. And many of that, what I'm trying to say in the next 45 minutes or so, is really in this spirit. Model theory is a vast enterprise, and so for the part that I want to discuss here, Chris Miller wrote a very influential paper in the early 2000s, and this is really the abstract, and I think this abstract is still better written than anything I can say. So I also want to cite this abstract from 2003 because it's essentially the same abstract for my part of the credit course that we teach. So what Chris wrote back then was that what might it mean for a first order expansion of the field of real numbers to be tame or well behaved? In recent years, much attention has been paid by model theorists and real analytic geometrists to the o-minimal setting. No, this was 20 years ago, and this I think is still true, hopefully. But there are expansions of the real field that define sets with infinitely many connected components, yet are tame in some well-defined sense. The analysis of such structures often requires a mixture of model theoretic, analytic, geometric, and descriptive set theoretic techniques. An underlying idea is that first order definability in combination with the field structure can be used as a tool for determining how complicated a given set is. So more or less, this is what I'm now going to elaborate on in the next 40 minutes or so. I do want to point out, and I think I go to great length and making sure that this is clear from what I'm going to do, is that, so maybe I highlight this here, the analysis of such structures requires a mix of model theoretic, analytic, geometric, and descriptive set theoretic techniques. So while this kind of enterprise, I think, is born out of model theory, it's really, I think, an enterprise in geometry, and I will try, as many of them before, to not use any kind of logic, even if sometimes it's really helpful to do so. Okay, so I think what I first want to do is again define a structure, and this, I think Chris did this 2 hours ago, but I will again formulate this here pretty quickly. So the kind of the main actor of our story is that we want to do definability, as model theorists call it, on the real line. So for that, and this is the way it's usually defined without using first order logic, is that if you take a structure to be a sequence of Boolean algebras of various r to the m's, so see this Sm is a Boolean algebra of r to the m, and you impose certain closure operations. So you say that if x is an Sm and y is an Sn, then the Cartesian product is an Sn plus n. Furthermore, we ask essentially the diagonals to be in there. So if you have I and j smaller than m, then you want to have the set defined by xi is equal to xj. Furthermore, and this is the crucial part, you want to make sure that not only is each Sm a Boolean algebra, we want that all these Boolean algebras together are closed under projections. So if x is in Sm plus 1, then the coordinate projection to the first m coordinates is in Sm. I also want to impose here directly from the start that the order relation is in this structure, and that all singletons in R are in the structure. Okay, so this is kind of a common theme of describing definability without first order logic. There are various different ways of doing so, and I think hopefully I've found a correct and equivalent one. So now what I want to consider, so essentially what this defines is structure just where you have order, but I want to add more, and I want to keep this kind of separate, what I exactly add, more algebraic operations. So one of the ways that we call this a K geometry is if they take a subfield of R, let's say K, then I call it K geometry is a structure which is closed under images of linear maps. So essentially what this means is that if you think about this as a model theorist, that you're allowed to multiply by elements of K. So you have scalar multiplication by K. And then I call something a field geometry. So that's really the field setting if you're closed under polynomial maps. So that if you have to define, if you have something Sm, and you have a polynomial map from Rm to Rn, then P of x, so the image on this polynomial map, is also in Sn. So again, field geometry means you work over the field. K geometry, that you work over essentially with a vector space given with a K vector space. We say that a set belongs to S if it is in some Sn, in the appropriate Sn. Sometimes I would say that S contains X, or to use the kind of model theoretic notation, I say that X is definable in S. We sometimes also say that X avoids, though that S avoid X, it simply means that it's not in there. Okay. If you have never seen this before, of course, many of you are expert, but this is really, this is for graduate students. So we should give the kind of standard examples of the kind of geometries we're thinking about, the simplest ones. So the first thing I want to kind of, and the example I want to give you is K semi-linear geometry. So in this case, you take K to be a subfield of R again, and the collection of all K linear semi-linear sets are the sets that are finite unions of this form, where the Fi's are Kf and the Gi's are affine K affine functions. And the statement of this example is that this forms a K geometry. The main thing, and this is always in these cases, is that of course this is is not how to see that each Sm in this case forms a Boolean algebra, but the hard part, and this is to show that actually this collection is closed under all projections. And this is essentially, if you think about this for a little bit, this follows from the very traditional Fourier-Motzkin elimination method. In this case, I mean, just to give you an indication why we call this a geometry, this contains, among other things, a class of a whole K polyhedra. And the next, so this is kind of the baby example of a K geometry. The baby example of field geometry is, of course, semi-algebraic geometry. Here we take the set of what's called semi-algebraic sets, and that is that are finite unions of sets of this form, where the F, the G1 to Gn are polynomials. And so this collection of sets forms a field geometry. Again, the main thing you have to show in order to prove that is this collection is closed under projections. And this is, again, very famous, the Tarski-Seidenberg theorem. Of course, and this is kind of where all this program comes in, is that you not just want to consider these kind of geometries as some kind of minimal geometries, if you like, but you want to extend them by further functions, predicates, whatever, sets in general. And so one of the main results that I want to state here is just that this what's called sub-exponential geometry. That's a collection of all projections on the first n variables of sets that are solution sets of polynomial exponential equations. These sets form a field geometry, and in this case, it's not so hard. The problem is not showing that this collection is closed under projections, because it's a collection of projections, but rather you have to show that it's closed and that each of these SMs form a Boolean algebra. So in particular, you have to show that the complement of such a set is again such a set. And this is Wilke's famous theorem, of course. So these are kind of the gives you, if you've never seen anything like this before, this gives you the kind of examples of geometries. All these geometries here have something in common. And what they have in common is they all satisfy a common notion of tameness, long ago invented by Lau, that we call a structure o-minimal if every element of S1, so all these elements that lie in R, is a finite union of intervals and points. All these examples you have seen, and a few more, are o-minimal. So semi-linear geometry, semi-algebraic geometry, sub-exponential geometry, something I didn't define globally, sub-analytic geometry, and so on. They are all o-minimal. There are various important consequences of o-minimality and striking applications of it. However, this talk is not about o-minimality, it's about beyond o-minimality. And so if you want to know more about o-minimality, you have to go to Gareth S. Jones' talk, which will be on, I think, on Friday, if I'm correct. So really what I want to talk is about geometries in general. And so really the naive goal of this kind of enterprise is the following. And it's really naive in this kind of most ambitious way. What I want to do is I want to classify all possible geometries, so that it be K geometries or field geometries up to equality. The model theorists, what this might be called, this up to interdefinability. But if you just look at the definable sets, that's the same thing. So this is the kind of naive overall goal of this research enterprise. Maybe before I go into this, really what you should know is not only that so far we always have given you the kind of geometries and claimed that they are indeed or it's this collection of sets, and I claimed that they are geometries. However, of course, what you can do is you can start with an arbitrary collection of subsets of values up and to the end, and then simply close them off under all these operations. So what I now want to define is, say, if you have any collection of subsets of values down to n, then let SA be the smallest structure containing. Of course, you can also say something like, take the smallest K geometry, or say take the smallest field geometry, just take the smallest thing that it generates. Of course, logicians, or many of you know model theory enough to, or logic enough to see that really what this means is that the sets in this structure are really just the sets definable with parameters, of course, in the expansion of the real line by predicates for the elements of A. The examples we have seen can be recovered. For example, if you take A sublinear be this set that simply contains a graph of addition, then the structure generated by that is just a collection of all Q semi-linear sets. Or if you want to put it in terms of geometries, it's just a Q geometry generated by the empty set. Similar, if you to the addition now add multiplications, the graph of multiplication, we now have addition and multiplication, then the geometry generated, or the structure generated by that collection, is a collection of all semi-algebraic sets. And again, if you want to think of it as what geometry generate, this is the field geometry generated by the empty set. And then similarly, if you want to get back to sub-exponential geometry, you let AX be the collection where you add to this collection from 2 the graph of exponentiation, and then you generate all those sets, and you get all sub-exponential sets. And of course, again, it's kind of one of the kind of things how you should think about the examples from the previous slide is that the point that these collections of sets form a geometry says precisely that if you generate them this way, this generating process stabilizes. For example, if you take the semi-algebraic sets, you don't have to keep closing under projections, because semi-algebraic sets are already closed under projections. Okay. So if you let me rephrase this kind of naive goal of classifying all geometries, then maybe if you think of this as structures that are generated by collection of sets, that really what this is rephrased means that given such a collection, you really want to understand the structure it generates. And so you really want to be able to compare them and say, given this A, are they the same or not? Okay, so even if I didn't introduce too much about o-minimality, so far I've only given you examples where the structure is o-minimal to satisfy some kind of nice conditions. Of course, in general, there's no reason that if you take an arbitrary collection of that you should again get something reasonable. Even if you take something which looks reasonable, then this might not create something reasonable. So for example, the standard example is if take the integers, add them to the graph of addition and multiplication, and ask yourself, okay, what kind of structure do you get? So if you think of it, this is, you take the integers and consider the field geometry generated by the integers. So you take this arithmetic object and you ask yourself, okay, what is the geometry it generates? And maybe not also surprising, it generates something extremely wild. So you can, with a little bit of work, and you're probably using Gödel's coding, show that this contains all closed sets. So the structure generated by the integer contains all closed sets, and even all Borel sets. And once you have all Borel sets, then you know that they're supposed to be, you have to take projections, and Borel sets are not closed on their projection, so you get analytic sets. But then you have to take the complement again, and you keep doing that forever. Because you have to take the complement, the projection, complement, projection, and this generates what's called every element in the projective hierarchy. So you get more complicated sets at every step. There's no uniform bound on the iteration you need to generate all these objects. In particular, from a geometric point of view, I mean, even all closed sets. That means what is all space filling curves? I mean, that's kind of close. The graph of a space filling curve should be a closed set. Are defined in these objects. All nowhere differentiable continuous functions are defined because all continuous functions are defined in there, or are in this collection, or in this structure generated by the integers. So really, from a geometric model theoretic point of view, or a tame geometric point of view, this is not tame. This is really as wild as you can be. So if you want to study all sets defined or that you get in the structure, that's really too much to study at once. Of course, I mean, if you think about what do descriptive set theorists do, I mean, they study projective sets, and so but what they do, they restrict themselves to maybe Borel sets, maybe closed sets, maybe Sigma sets or something like this, but they study only parts of it, not the whole structure. Okay, so there's clear wildness beyond o-minimality. So there's structures which are not o-minimal, which are not these kind of nice geometries that are well studied. There are things that are clearly without the reach of any kind of geometric methods. However, there are many examples, and the most classical example, or the most important example, is due to Chris Miller and Patrick Spizak, which is the logarithmic spiral. So if you so let S sub omega be the logarithmic spiral, which is drawn over here. And if you want to know what the kind of precise formula is that defines this very nice object, it's here. What they showed was that every set in that is in the structure generated by that spiral, while it's not o-minimal, so while there are infinite sets without interior, every set in this structure is a union of an open set and finitely many discrete sets. So that's the property that nowadays is called almost de-minimality. So in particular, what you can get from that is that the integers are not definable. Okay, well, you have to do a little bit of work because the integers are a discrete set. But you can say if you have the integers, you define all kind of closed sets, and you define surely also the rationals because you have the fields around and you just take the proportions of them. So you get from the fact that the rationals are not definable, you get, or they're not in the structure, you get that the integers are not defined. So overall, this is kind of the prototypical example. And Chris, I'm pretty sure talked more about this 2 hours ago. Is this example of a tame structure that is not o-minimal. Note, and I want to point this out here, so I think this is important, maybe not for this talk, but definitely for the graduate course, is that if you look at the projection of the spiral onto the x-axis in this picture, then this is this set e to the 2 pi z divided by omega. And this is a discrete set, but you see one of the important difference between this set and let's say the integers, which are also a discrete set, is the growth rate. I mean, you see that the kind of the growth rate of the set or of the spiral, if you want to see it this way, is exponential, and this makes all the difference. And we'll see this again and again. Okay, so I had this kind of naive goals at the top. So now I want to make this slightly more reasonable, given that we have now seen that there's certain things that are wild, there's certain things that are maybe not o-minimal, but still somewhat tame. So a more reasonable overall goal, a more reasonable shorting goal in the sense of that this is about shorting tame mathematics, is that we want to classify these geometries, maybe not up to equality, that's maybe equivalence relation too strict, but rather up to some kind of common tameness conditions. So maybe we'll say we want to classify it all up to all d-minimals. So some are d-minimals, some are o-minimals, some are wild, and some are maybe somewhere in between. So the overall goal, and I think this is now really, at least for me, an important part of this tameness program, is to really find out what is the landscape of these geometries, in particular beyond o-minimality, but maybe below this wildness that you have when you get the integers and hence the whole every Borel set, every projective set. Okay, so one condition I want to talk about and is now, so we have this wildness. We have this wildness when you have the integers. Can you somehow get some tameness out of it when you not get the integers, when you don't have the integers in your structure? And for that, I will have to introduce something which might look very kind of technical, but it's really, this turned out to be the kind of right notion to consider. So what I want to introduce here is I want to talk about a linear order. So linear order is, of course, a set with some kind of linear order on it. And for this talk, really what I want to consider is subsets of the line. So you'd say you have a subset X of the reals and a linear order on it. We say that this linear order belongs to the structure. Model CS would say it's definable in that structure if X and the order as a subset of the two belong to the structure. I don't want to consider just arbitrary ones, but rather special ones. So we call such a linear order a dense omega order if this X as a subset of R is dense in some interval, okay, dense in a usual topological sense, and the order is order isomorphic to the naturals. So something like order type omegas, I think the fancy word for it. And so why would you consider such things? So the main point is that this gives you a very good condition that guarantees, let's say, a sufficient condition that for wildness, so that you get a Z in your structure. So let's S be a field geometry. If this field geometry contains dense omega order, then the integers belong to this structure. So that really means that not only the integers, but once you have the integers, you also again have all closed sets or Borel sets and all projective sets. So from a model theory or from geometric point of view, this is a really wild thing. Of course, why bother with this kind of technical condition? For two reasons. First, for one, it's kind of the dense omega orders appear rather naturally. For example, when you have a function that maps a dense set onto a somewhere dense set, so if the graph of that function is in your structure, then you have a dense omega order. So if you can somehow think of this as if you can collapse a discrete set to a dense set, then you can show that you have a dense omega order. And that happens more often than you think. So it really is it's a nice sufficient criterion for wildness, because there are many examples where it's satisfied. I think Chris has mentioned them, might have mentioned some of these, or might mention some of these in his talk, in his graduate course. But also the other way around is rather powerful. So not only does the existence of this gives you something wild, the non-existence of such a dense omega order in a geometry has substantial consequences on its own. So part of it is why we're interested in that, because that even this kind of non-existence allows us to understand the tameness of this structure. For that, I just really briefly want to recall some notation or some definition, first introduced, I think, by Miller and Speisecker in a slightly different form, but then again by Dulwich, Miller, and Steinhorn, is the notion of a d sigma set. So really, if you can follow this definition here, because it's too technical, then really what you should think of this is a definable analog in some sense. One has to make this precise because there are many very different ways of defining this. This is the definable analog of an F sigma set. Okay, and so what this really just says is that this set is d sigma if there is a subset of Rn plus 2 in this set such that X is a union of this Y sub Rs. But of course, Y sub Rs is supposed to be that you fix the last two coordinates of Y with R and S, and this is everything above this. So this is, what is it? Something YRS, I write this down here, is just all the X such that XRS is Y. And so if these sets, if these YRS form an increasing family, okay, you have to say what that increasing decreasing family. So what that means that if you increase R, then the set becomes larger. If you increase S, the set gets smaller. And if X is the union of such things, I'm missing closed, right? I'm sorry. All of this will be closed. Then sorry, yes, what the YR should also be closed. Then I get a DC. Then this is a D sigma set. So it's a kind of definable union of these kind of closed sets. And so, why do you care? So what we get in this kind of setting where you do not have a dense omega order is the following. So let G be a let S be a geometry that does not contain a dense omega order. Then the following is true. I somehow consider the statement here as, we say, I call this strong back category theorem, but you should really think of this as a geometric kind of tame back category theorem. So then every D sigma set either has interior or is nowhere dense. Why is that relevant? I mean, think back to what the bare category theorem gives you. It gives you that every F sigma set either has interior or is meager. So this kind of nowhere dense just gives you meager, but meager is dense and codense per se. So this is, I mean, it doesn't tell you something really geometric in some sense, because it really just says it's small in this kind of descriptive set theoretic way, but that we cannot really grasp well in this kind of model theoretic geometric way. However, here we get that this has to be small in a geometric way. And so this is really the key point where all this kind of works out, is that this kind of, we get the stronger bare category theorem, this kind of geometric bare category theorem, and this allows you to develop in some sense a more geometric descriptive set theory in these structures. At least tame geometric descriptive set theory in the structure, which allows you to prove many results, and some of them I will discuss in the graduate course. Okay, but let me kind of put this in kind of a larger context. So I mean, I really remember the one thing I want, and I still have this at the top of the slide, I have this kind of charting book, classify geometries up to tameness conditions. Okay, so let's see whether I can, after a couple of definitions, whether I can kind of draw a picture of this kind of a priori vast space of different geometries. So this is really nice, this kind of this picture which I will draw in a minute, and this kind of definition, this trichotomy, or later tetrachotomy, is really an idea of Eric Waldsberg. So he said, okay, let's introduce, so if you say that not if getting a dense omega order is something tame, then let's give this a name, let's call this type A. Then we said that if you have closed sets or even just compact sets, then you get all these bad things, and you get all these bounded Borel and bounded projective sets, then you're in a really bad shape. So let's call this type C. And then let's also introduce some type B, which is neither type A nor type C. Of course, this gives you a trichotomy because you define it to be a trichotomy. But I will give this a more meaning in just a moment. So but one more thing I need before I show you the picture, and you already see it, is I also want to not only distinguish between these tameness conditions, but I also want to distinguish here just for a moment about, let's say, whether or not you have a field around. Again, a very classical question in model theory, if you want. We say geometry is field type if there's a field in that structure on some interval. So if there's a field on some interval of R, such that it is a field, and both the relations, the addition and the multiplication, are in the structure, so they're subsets of R3, so as subsets of R3, and moreover, this field with the order, and with the usual order on R, is isomorphic to the real field. So locally, there's field structure. So now Eric's idea was essentially this following picture, and I will discuss somehow. I'm going to talk a little bit about this. So the main thing we saw already is that this kind of the dense omega order. So if you are field type and you have a dense omega order, then you're in this kind of type C. Then you have all these kind of compact sets. That was this kind of fact that I stated on the previous slide. In particular, if you want to phrase this in terms of continuous functions, let's say, and what this means that every continuous functions on a compact domain is in this structure. So if you're type C, that means and you surely have all of that. But if you don't define the dense omega order, and you are field type, then as I pointed out in the previous slide, then you have this kind of strong back category theorem. And with that, you can get to work. And with that, you can really start talking about getting results from o-minimality, or some kind of generalization of results from o-minimality that holds in this kind of larger context. If you want to state this in terms of continuous function, for example, one result that you get in this vast generality is that for every continuous function in this structure is CK almost everywhere. And almost everywhere means here, and for this purpose here, means on a nowhere dense set. So I was outside the nowhere dense set. So this is kind of classical result for o-minimal structures that I mean that outside a finite set, every continuous function, let's say from I should say maybe from R to R, every function is CK outside the finite set. And this is kind of the generalization. I do not want to talk too much about this, but since the graduate course will be more about when you have a field around. But I do want to point out, see, that really it's kind of interesting if you know that you don't have a field around. So in that case, I mean, many things could happen. I mean, you could still get some kind of weird functions or so that they might be not linear, but also you don't see the field. But no, that's really not the case. So if you don't have a dense omega order and you don't have a field type, then every continuous function is affine almost everywhere. So even here you have this kind of, in this kind of setting of type A structures, so this kind of where you don't have an dense omega order set, you have this situation, they have this kind of I mean, some version of the Peter-Sitzer-Senko trichotomy for o-minimal structures you have even in this generality. Then there's, of course, before I talk more about this detail, I want to mention, I will come back to that for a second in a moment, because there's this kind of, there's also types B, which is where you define a dense omega order but don't have the field around, essentially. In that setting, and this is really closely connected to what Ian said today and what Lexi will talk about on Wednesday, and we'll say a bit more later on. But for now, this is a kind of the linear setting where you have a dense omega order. It's a little bit better because, for example, what you can show there is that every C2 function in such a type B structure is affine. So you really have this kind of tetrachotomy for expansions of the real line, or for this kind of geometries. But really what I would care about in my graduate course, and it's already what I want to develop, and I'll say a little bit more about this on this next slide, is really this case and even just some part of it. So this kind of type A structure of field types. I want to look at this kind of type A as a very general tameness condition, and I will study them. And then also, and I will do this on the next slide, do a more in-depth analysis of the kind of tameness notions within this type A. Okay, maybe that's what I want to do next. I want to talk a little bit about, let's say, you know, that some of these tameness conditions we have seen, o-minimality, de-minimality, how they fit into this picture. And how they fit is that they're actually all type A. So what we have seen so far is that that if you have a field geometry, then either it's type A or type C. This is actually, you can even strengthen this a bit, so that that means if you have full multiplication around and you have this tensor omega ordered set, then you're either type A or type B, as type C, so the type B case falls out. Or if you, but this can even strengthen, you don't need the full multiplication, or you really just need the R vector space around, then there's no such type C. But I really, what I want to get to here is the following. If so, you know, these kind of, you can come up with a tameness condition. Well, there's kind of 30 or 40 years of tameness conditions over the real line. And all of these tameness conditions, all of them imply this kind of more general condition of type A. So if you take o-minimality or de-minimality or any other, I mean, I would say a little bit about this, but I mentioned this now already, de-minimal open core, locally o-minimal core, locally o-minimal, o-minimal open core, all these kind of tameness notion that anyone has ever proposed in this setting, these are all generalized by type A. If you are a model theorist, so you care more about this kind of geometric combinatorial, about this more combinatorial kind of tameness notion, then also this is all type A. So if structure sets, or this kind of the corresponding expansion, of course, there's by any kind of Scheller-style combinatorial of the tameness notion, like distality is very on vogue, NIP, NTP2, they are all in this type A structure. So for me, the motto here is that, and that's why I also want to kind of understand it. Type A in the setting of the real line of the real geometries is the ultimate generalization of o-minimality. And so what I want to do in this kind of graduate course, I will develop this kind of theory of type A field geometries, but it will also be with a strong focus on studying kind of strengthenings of this kind of very general condition that are in between o-minimality and this wildness. So I think they will naturally talk about the minimality and related tameness notions. So if you let me draw this picture one more time, so I now want to kind of come back to this picture, this tetrachotomy, but this time I want to talk a little bit more in depth about, let's say, the kind of various different tameness notions and where we currently at. So if you look at this picture here, this is again the same tetrachotomy picture. Again, really, as I said in the graduate course, the part that I really care about is somehow this part here. And what you, maybe just this part here. What you can see here, so as I said, this type A part generalizes the kind of known tameness conditioners over all of them, but I didn't write all of them here. So for example, o-minimality, locally o-minimality, if you know that, and it's just every set is a finite union of, or the union of a finite set and of an open set and a discrete set. Then de-minimality was a finite union. Every set is a set of the open set and finitely many discrete sets. And then there's this kind of the most kind of natural generalization that you could ask in this setting is something that I think Chris came up with the name. Is noiseless, and so we call the structure noiseless if every element either has interior or is nowhere dense. So it's, I mean, if you think about, you can, I mean, all these kind of different tameness notion here, they're always of this form, either the set has interior or something. So o-minimality is either interior or finite. Locally o-minimal, I said, is either interior or discrete. De-minimal, okay, modulus something, is either interior or finite union of discrete sets. And then noiseless is kind of the weakest form you can ask in that sense, is either has interior or is nowhere dense. Okay, so this is kind of the picture you should have in mind. There's one important thing that I haven't talked about, and I will do this on the next slide, and then I'm close to finishing, there's this notion of open core I mentioned. And I want to come back to that just for briefly, because it's very important for this picture. So if I come back to the picture the last time, I'll go and introduce the notion of an open core. A very natural thing in this kind of setting, and was introduced by Miller and Spydecker. If S is a structure, you can take the subcollection of all open sets in this structure. That's not the structure per se. It's not a structure, but the you can generate a structure using that. So the open core of a structure is a structure generated by the open sets. So this gives rise to many new tameness conditions, like you can say maybe the structure is not o-minimal, but the open core of the structure is o-minimal. The d-minimal open core, the open core of the structure is d-minimal, or the open core is noiseless, or so this every tameness condition we had before, you can kind of put on the open core, and that gives you a tameness condition again. Note that all of them are still type A, so I'm still not leaving type A structure. The canonical example, and I think Lau is the one who proved this, so the open core of the structure generated over the field by the real algebraic numbers. So this is a set of all real numbers that are satisfy a polynomial with rational coefficients. That the open core of that in our notation is just semi-algebraic geometry, and hence o-minimal. So that is a classical example. But actually, I'm not so much interested per se about for this kind of topic, or for my talk about the open core. What I'm interested in is something that I definitely like, but I think other people too like to call Miller's conjecture, which is that if you take a field geometry and it does not contain Z, then the open core of the structure is noiseless. I'm pretty sure that that Chris wouldn't say that this is a conjecture. I think he would only ask it as a question. I hope it's true. I think I'm probably also more optimistic that this is true. If it's false, it's my fault. Then blame me calling this a conjecture and not Chris. You can put this in a stronger form. So what the stronger form really is, and this is kind of is that not only you want to have, let's say, field geometries that do not define Z, but really any kind of geometry that is type A. If this is type A, so if it doesn't define an omega orderable set, then the open core should be noiseless. Okay, so we're still talking about open core, and this open core might look like a technical condition, but it's really, I think it's a very, I think maybe the following form shows that it's not, but it's really the one thing that one wants to consider. So to consider, so you could take expansions by, of course, arbitrary sets, but of course it's very natural to consider geometries or structures in general generated by just open sets or by closed sets. I mean, if you take a structure generated by the closed sets, then simply take the complement of these sets and take the structure that's open, generated by these complements that are open. So if you restate this conjecture, this really just says if you take all the structures that are generated by open or by closed sets, then this structure is it's type A, so it's not wild, then it's noiseless. So that means if you start without any kind of noise in your structure, and many of the in this kind of tameness program or in this kind of real analytic program, of course we don't take this kind of noise structure. We take objects that do not have this kind of noise. At least most of then this structure has to be noiseless. So if you want to draw this here really in this picture that I've now showing you for the third time, really what this conjecture says is that this is the picture for structures generated by open sets. So what this would mean is that if assuming this is the strong form of Miller's conjecture, you would have this kind of tameness, this type A structures on so this kind of on the left hand side, but we have this kind of o-minimality, all this kind of tameness notions, which are kind of strengthenings of this kind of noiselessness. But that's it. So all these kind of tameness notions that we have now been studying for many years are really just something like okay, noise is a set union of an open something that has interior or is nowhere dense. And so all these other ones are just kind of strengthening where you say more about this nowhere dense business. And even if you would prove something like this, what I would believe it would, if you can prove this kind of conjecture, it not only would give this kind of nice picture, it would also be kind of give us a better understanding of where all these kind of tameness notions come from. Because you would really kind of, you would probably have to prove some kind of very general tame cell decomposition theorem for these kind of noiseless structures. And maybe all these kind of different cell decomposition theorems that you know for D-min, O-min, and so on, they would really just be specializations of these kind of very general theorems. So I think even if you don't care per se about this this very general kind of classification program of tame structures, I do think this will, if proven correctly, give you some kind of insight of the structures, of this kind of o-minimal structures.
Okay.
I think they asked something. Okay.
Okay.
Okay. Sorry. Let me answer Alex's question. I'm almost done. Then I answer this question really. So before I finish, so I want to. So this kind of this kind of general tameness I want to study in the kind of in this graduate course. I do want to point out, so I said that I wanted to say two things about the type B structure. So these kind of type B structures are kind of weird. There's a good reason for that, or at least from examples of such, and I can give you rather natural examples. For example, you take the usual ternary middle third Cantor set. Then the Q geometry generated by this kind is a type B structure. So that's, I mean, Alexa will talk more about this related on this kind of on Wednesday. So in this kind of settings, you can really do some kind of metric geometry that you couldn't do in this other setting. But this comes at a price. Then the second example is that if you take a quadratic subfield of R, which is not just the rationals, then the K geometry is generated by Z is type B. Many of not all examples of IN, but the kind of the where he considered a quadratic alpha. I think that was the letter used. These are definable in this structure. So this kind of structure, while type B carries a lot of number theoretic information about this quadratic subfield, in the sense of the BT sequence of the Sturmian words and so on. However, while all these geometries I mentioned here are really not satisfy any model theoretic or geometric tameness in the classical sense that we study it, the theories in the terms of model theory of these are all decidable. So decidability here is not this kind of the tameness notion we study, and it's not just restricted to type A. So decidability for that is really different kind of animal. Okay, and so then this is really what I want to finish with. So I said this is an invitation to the graduate course, but it's also an invitation to this research area. For me, the job description for model theory or tame geometry in this kind of area is really, I mean, as Lau wrote in the beginning, is discovering and charting. For discovering, I think of this as determining whether a collection of sets generates geometries that can be considered tame, and maybe what that tameness condition is they satisfy, or but precisely that what is precisely the collection they generate. The charting is what I have done here in this kind of pictures, or I try to do in these pictures, is the understanding of these various tameness conditions, how they relate to each other, how they cover it, how the kind of the overall picture of this landscape look like. I want to finish here with a citation actually of Anand. I'm sure he didn't mean it this way, but I'm gonna interpret it in precisely this way. So what he wrote, and I hope that this fits kind of the narrative I'm trying to have here, is that contemporary model theorists tended to concentrate on the tame regions of mathematics. Maybe think of this as o-minimality, or the exploration of the borderline or the middle ground between tame and foundational theory is a fascinating topic. Foundational here means this kind of wildness. And so I hope some of you might enjoy the course I'm going to give, Chris course. And as I said before, if you're interested in talking to me about this, I would be very happy to. So thank you very much.